So we'll see TPS. It's been added with the map, added with engine, ego, then easier. Here engine control. The map is been added to this. This is added to this. Then here a fuel injector, an ignition system. So this has been all added to this, and the ego is being sensed again to this. And we have see the crankshaft here. Then coolant temperature. Coolant temperature sensor. It's also been added. This is the figure with respect to electronic engine control system. Okay, so here this all the superset of variables being sensed in engine to control, including the following parameters. Okay, so here the sensor what we're going to use to determine the oxygen concentration, that is exhaust pipe heater, control for electronics reference cell with reference air passage, diffusion gap, then oxygen pump cell, gas, IP pump, UP pump, UH heater, reference voltage and sensor voltage. If you know in-depth discussion between the exposed sensor. Okay, here we should correct the operation of electronical controlled engine operating with government regulated exhaust emission requires the measurement of mass airflow, that is MA, and this is mass airflow into the engine, and the categorization component, a CAT component for short term average, where at interval tau, that is MA tau of T equal to 1 by tau integration of T by tau T MA T cap of one derivative. Okay, so here the tau is the interval that having long suppress over the continuous time, and MA is the mass acceleration related to revolution per minute, and time varying component with respect to the lower cylinder pumping frequency, exhaust with RPM, and alternately the steady component over the mass airflow can be represented by low pressure filter version of instant flow rate that is we call already we discussed, that is transfer function in open loop and closed loop. That is h of LPF is nothing but h of LPF of S is equal to B naught plus B1 S Bm S of M divided by A naught plus A1 S plus AN Sn, where the coefficient determine the response characters of the filter and the filter bandwidth effectively selects the equivalent time interval over with the mass airflow measures with respect to the average. And the typical MOP sensor is a variation of classical airflow sensor that was known with the hot wire, which can be used, and it is going to measure the wind velocity of weather forecasting and all. And the changes in position to the heat removed by the air system, producing the changes in resistance. The convenient model of sensing elements, that is RSC, at a temperature T is given by Rs of capital T equal to R naught plus Kt of dou T. So here R naught is nothing but a resistance at same frequency with reference to temperature, that is T ref with 0 degrees Celsius, and dou T equal to T minus of T reference, and Kt is the resistance or temperature coefficient for conducting sensing element Kt greater than 0, and for semiconducting sensing element Kt is equal to 0. So that the mass airflow of the moving stream is measured by the measurement of the change in resistance, which is defined by the bit circuit that is this R1, R2, here V1, so R3, and here there is a pulse. So it is being given as non-negative terminal, inverting, non-inverting terminal, and the same is going to be given to op amp, that is inverting and non-inverting terminal, and here we are going to get V naught, and it is being get feedback to open loop. This is a bit circuit. So here is going to flow V naught equal to G of V1 minus V2. This is V1 minus, this is V2. Okay. So the delta V equal to V1 minus V2. There is small change with respect to that bit circuit. Okay. Now if you try to see the overcross voltage with respect to the resistor which is connected in parallel, so R2 divided by R1 plus R2 minus of RSC divided by RSC plus R3. So if V naught is equal to G delta with respect of V, so 1 by G uh, equal to R2 divided by R1 plus R2 minus of RSC divided by RSC plus R3. So if the MF sensor configuration is assumed and the G is lesser greater than to 1 with a large G and RSC is approximately given by RS of T equal to R2 minus R2 into R2 0 by R1. And after that, if the constant voltage being specified, that is KT equal to dou of T equal to R2 by R3 divided by R1 minus of R0, R0 plus KT of TA, T reference, where R2 KT of 3 divided by R1 equal to KT. So delta T with respect to measurement of small change is 1 by KT, R2, R3 naught divided by R1 minus R0. So at last, if I try to cross the voltage difference in between this, so if PSC equal to I square R loss, then V naught divided by RSC plus R3 to the whole square RSC. Okay, so V equal to V naught of MA is being analyzed as V square naught plus K MA of MA 1. So if I try to see analysis character of this with respect to the graph, that is mass, airflow, rate, that is G per second versus P naught. So 0, 0 0.5, 1, 1.5, 2, here 1.5 to 2, 2.5 to 3. So it starts from 0 0.5 and it's been get very. So means output voltage tells about MAF versus mass flow G per S.